My name is Nyambura. I'm presenting the introduction for the Group 5 project. Our project was aimed at developing a biosensor technology that detects water contamination. And my fellow group members are Tanui, Shadrack, John Adam, and I. Our objective, as I said, is to develop a biosensor technology that detects water contamination with Vibrio cholerae and Salmonella typhi. This is because of the rise in waterborne diseases and the fatalities associated with them in the peri-urban areas and the refugee camps in our country, Kenya, caused by these two bacteria, which is a major challenge to the public health. Next. With our biosensor, it will be based on monoclonal antibodies for the two bacterial agents, which we will develop and optimize using the AlphaFold technology. And for specificities, we will screen for their specificities to ensure that they are not cross-reacting. There is no cross-reaction with other antibodies from antigens from other pathogens, so that we make sure our biosensor is highly sensitive and highly effective. Also, with this technology, the biosensor will be on site. This way, you would have to collect a sample and take it to the laboratory. You can test it on site and save time and lives at the same time.
Okay, so my name is John Adams, and I'll take you through the rest of the methodology. So to begin with, we will use a couple of tools to develop the monoclonal antibodies, among which we will use BioBricks, which is a bioinformatics tool to design and construct the genetic constructs that encode the monoclonal antibodies. Also, we will use benchling to perform in silico validation, where we will simulate the assembly and expression of the monoclonal antibodies in the host organism. We chose our biosensor will use electrochemical signal as the mode of detection rather than colorimetric and other methods. So when the target pathogen binds to the monoclonal antibodies on the surface, the interaction induces a change in electrochemical properties, which is then detected. We will use a couple of methods to bind the antibodies to the sensor, such as covalent binding, and common materials that are used to achieve these are gold nanoparticles, carbon nanotubes, or graphene. In addition, we will have to amplify the signal so we can get as accurate as possible the results, through which we'll enhance the signal using enzyme-linked amplification techniques to improve detection limits and accuracy. So the enzyme will be conjugated to the antibody, and we chose to use horseradish peroxidase along with its substrate TMB. So the methodology has a specific strategy which makes it unique to other biosensors. We decided to call it the dual target detection strategy, which means the biosensor is able to detect both Salmonella and Vibrio in contaminated water simultaneously. Yeah. And among the materials that we'll be using, are monoclonal antibodies. The specific names are provided over here. Together with the links, you can visit the registry, and we will use gold nanoparticles to immobilize the antibodies, and we definitely will use electrochemical detection setup electrodes. All right.
So my name is Tanui Shadrack. I'm going to discuss the results, conclusion, and the recommendation. So the biosensors performance will be evaluated by testing its response on the firing concentration on the Vibrio cholerae and Salmonella typhi. That includes the sensitivity, specificity, detection limits will be determined through the following techniques. So sensitivity will be determined the lowest concentration of Vibrio cholerae and Salmonella typhi that can be detected by the biosensor. Specificity can be evaluated, ability to distinguish between Vibrio cholerae and Salmonella typhi and other non-target pathogens to minimize false positives. Detection limit, establish the minimum and the maximum detection limits for both pathogens to ensure accurate reading across a range of contamination level. Next. So the response time is the measure time taken by biosensor to detect the presence of the pathogens and produce a readable signal. And the field testings conduct field tests in various environment settings such as peri-urban slums and refugees camp to validate the biosensor performance in real-world scenarios, because that is where the most problem of cholera and typhoid occurs. Next. So the discussion, this is an example workflow of the discussion. So during the sample collection and sample preparation, you collect the water sample, followed by simple and rapid sample preparation method to isolate the pathogens from water. These include the pathogen concentration, use centrifugation or filtration to concentrate the pathogens, sensor interface, introduce the concentrated samples to the biosensor, detection, the biosensor detects the presence of Vibrio cholerae and Salmonella typhi through specific interaction with immunomobilized monoclonal antibodies. Signal processing, the sensor processes the binding events and translate them into measurable electrochemical signal. And then now there's the results display. The results are displayed using a friendly interface such as the LCD screen machines. Next. So the conclusion, we have the advantages. Comprehensive detection, provide a broader water quality assessment by detecting multiple critical pathogens. Public health impact, address a wider range of potential health threats, making the biosensor more valuable for ensuring water safety. Efficiency, it saves times, resources by simultaneously testing for multiple pathogens. It also reduces the cost and ease use. It is also small, portable, and biocompatible to the environment. While the geo-targeting biosensors offer significant advantage in terms of sensitivity, specificity, and rapid on-site detection, it also faces challenges to complexity, cost, and potential cross-activity. Competing technologies like PCR, immunoassays, energy have their own strengths and weaknesses. Next. So we recommend this after all the experiment. Continuous improvement, invest in ongoing research and development to enhance biosensors performance, including expanding detection capabilities to other waterborne pathogens, not only the Vibrio cholerae and Salmonella typhi, include other pathogens. Capacity building, provide training for local health workers and community members, and use and maintenance of the biosensors to ensure effective deployment and suitability. Policy support, advocate for the policies that support and use of innovative technologies like the biosensor in water quality management and public health initiatives. Data sharing and collaboration, establish platform for data sharing and collaborating between researchers, public health officials, and communication to track water quality trends and respond promptly to potential outbreaks. Next. Done.
Okay, thank you. We have come to the end of our presentation, and we hope you get the most out of it. In case of anything that you need, perhaps you could contact us via either of the emails provided over here. Bye-bye.